Section 6B is going to continue our discussion on the distribution of data. In 6A, you were introduced to the big three, the shape, the center, and the spread. But most of that section focused on the center, and by that I mean the mean, the median, and the mode. This set of notes is going to focus on the spread of the data, also called the variation. The first problem is going to be over our most basic way that we can describe spread of data. And this is something that you may have learned in grade school or in grade school or in junior high. And it's called range. Range, simply put, is the difference between the highest value and the lowest value that you have in a data set. So we had looked at these numbers before. These are Chief Justice ages. In the first six, the highest value that we have is a 59. The lowest value that we have is the 44. So if you were to subtract 44 from 59, and they show that over here, it gives you 15. And we describe that as the range of the data that we would have for those numbers. Okay, for the most recent six Chief Justice ages, the highest we have is 69. The lowest is the 56, and if you subtract those numbers, you're going to get 13. So again, this is a very, very basic way of describing how spread out the data is. If you get a small number, it would mean that the numbers are very close, and if you get something larger, then it means that they're far apart. There's positives to it, but the big problem is it doesn't tell you a lot about what's going on in between that high number and that low number. Okay, before we get into the rest of the activity, I wanted to show you these graphs and talk a little bit about where all this stuff is going to be going. One of the big things is that in the activity, you don't really get any graphics that look like this stuff. In 6A, we had pictures that we got to look at, and I think that those pictures helped out a lot with understanding why we choose the certain things that we do. So I'm going to give you a preview of basically everything that we're going to talk about as we go through the rest of this stuff. Okay, two main types of graphs that we're going to get for distributions that we look at today. You have symmetric graphs, which have what we call that bell-shaped curve to it. You also have skewed graphs. Both of these are going to be skewed to the right because they have that sort of tail that goes in that direction. Okay. From 6A, what we had learned is that if you have symmetric graphs, the mean, the median, the mode are all going to pretty much fall in the same spot. Now, the graphs aren't always perfectly symmetric, so they could be just slightly different, but for the main point, they're basically right there in the middle. So what we usually did to describe a symmetric graph is we took averages of numbers, which is called the mean. Okay, and then in skewed graphs, the mean, because you've got these they're called outliers, numbers that trail off to that side where it's skewed, those numbers in an average tend to pull the data too far in a direction. So what we do is we choose a number called the median, which would be located here. So the mode is always going to be under the high point. Kind of recall that there. The mean is going to get pulled further away from that high point. But the median is a number that's kind of in the middle, and what it does is it breaks your data in half. It's always finding that middle number. So we tend to use that one if we have skewed data. All right, so today, talking about the spread, we're looking at not just, okay, here's a number that describes the general set of data, something in the middle, but we need to consider how does the data look around it. Like in this first graph, everything's symmetric, right? Everything's symmetric there, but a lot of the data is pretty darn close to that center line. It's pretty tight in there. It trails off to the sides a bit, but it's pretty tight to the middle. But then you can have another graph that's also symmetric, except that the whole graph itself is getting pulled out. So if you're looking for like the majority of the graph, you might be grabbing all of this and saying, okay, well, that's the majority of it, where in here, the majority is much tighter to it. So we need to have a way that we can describe that tightness in the graph, and what we're going to end up using is something called standard deviation. If you have a skewed graph, again, this is a picture where everything's a little bit more tight. It's not as pulled to the side there, okay? And then this one, it's a bit more opened up, and it skews off further to that direction. Okay, the median is what we use for our center here. And if you're going to be using median because you have a skewed graph, the way that we're also going to be describing the spread, which gets introduced in this whole activity here, is going to be using quartiles. There's a lot of names that we could use for this one. We can use quartiles, we can use the actual graphical way, it's called box plots. And you can also refer to it as a 5-number summary. So there's a lot of names that go with it, but I just wrote down quartiles for that one. Okay, so as we go through things, you're not going to have the graphs to look at, but keep most of this in mind. Symmetric means use the mean and standard deviation, where skewed is going to say use the median and quartiles. Okay, so what we get to look at now is the reason why talking about the spread of data is important. I forgot to answer this question before I looked at the graph, so I'll just come back to it right now. It said to write 1 to 2 sentences using the ranges that you just found, that's the 15 and the 13, to compare the variation in the ages of the two groups. In my opinion, the way that I look at the question right away is they're not really that different. If you remember the data from beforehand when we looked at it, one of the main things is that these numbers were much lower than these numbers. But as far as the range, I don't think that they're really that different from each other. 2 years, like difference in age comparisons is like 13, a spread of 13 years versus a spread of 15. I don't think it's that much of a big deal. But we do want to address it. So you can write whatever you want in that spot. Okay, so here, this graph might be a little bit confusing, but we're trying to look at both sets of data the same so that we can do a comparison of their spread. And you'll get to see that the difference between 15 and 13, that little bit, that highlighted here just a bit. Okay, what I'm going to do is I'm going to cover half the graph because I think that might be helpful in reading what we're looking at. We can look at this as a dot plot type graph that we have for the first 6 Chief Justices. Okay, and that line that's in the middle is going to be the mean. So they're using mean versus median to describe the middle of it. And what we get to look at is kind of like how far the dots are from that spot. So even though that's our representative in the middle, you know, you've got dots that are over here and over there. That middle number doesn't really represent the majority of them. It just happens to be a number that's in the middle. Okay, and if you look from here to there, that's the spread, which is going to be the 15. Okay, all right, underneath that one, so all the data seems to like shift over, right? So now we're looking over here. Here's your mean. It is sitting pretty close to a couple of the numbers that are in there, which is kind of good because we didn't see it in the last one. Your spread is still pretty much the same thing, just not quite as wide as we saw, because this is only going to be 13. Okay, so now a comparison between the two of them. One thing that we really can take away from it, and I wasn't thinking about it until I started talking about it in this fashion right now, is that the first tells us that the mean is not really the best way to describe the data, because it doesn't, even though it's in kind of like in the middle-ish of the numbers, it doesn't really represent those in the group. But in the second graph, it does tend to represent a little bit more, because you can see it's right on 2 of those, and then there's a couple that are very close to it. Okay, but now their spreads are still kind of the same. So maybe what we don't want to just talk about is like how much the spread is, whether it's 15 or 13 or those numbers, but also to talk about what does it look like within that spread as well. Question 3 is going to get us closer to looking at how we describe data points with respect to that center number, the mean. And ultimately, it's going to get into something called the standard deviation. Let's see where that one is. It's going to get us to the standard deviation. Okay, the beginning to that calculation, which, by the way, standard deviation is a really like obnoxiously long thing to do, and well, I guess we'll talk about it in a little bit. But the beginning of how the calculation is done is you have to have a mean, you have to take an average, and that's this x bar. I think we did talk about that in 6a. Okay, so x bar, B-A-R, is just the averaging of all the numbers, which is 51.8. And this is for the first 6 Chief Justices. Okay, so we have that number. Then we're going to talk about what's called deviation. Deviation is how far you are from something. So we're going to look at how far each of these actual ages are from the mean. And you do that simply by subtracting. Now, it is important that you subtract in the right order here. you do have to take the value that you've got, the real value, and from that one, you subtract your mean. Take your number, your actual age, and you subtract the average of the ages. And you just do that with each one of these. Now, in some cases, you're going to get positive numbers, and in some cases, you're going to get negative numbers. Okay, and based on the graphic that we have at the front, we should be able to figure out why that is. If we're taking the value of the dots and we're subtracting the mean, if you take anything that is below the mean and then subtract that larger number, you're going to get a negative. If you take anything that's above the mean and you subtract the mean, you're going to get a positive number because you had a larger number. All right, so this question, consider the deviation for 44 years, right? And that one's already worked out for us. Write a sentence to interpret the deviation and why is it negative. That value, its deviation is, it's 7.8 years away from the mean, but it's 7.8 years below the mean. That's where the negative comes in. So this one's going to be 4.2 above. This is going to be 0.8 below. So that one's really close to it, but just underneath it. Okay, and then you've got pretty far underneath it. You've got pretty far above it, and so on. Question 5. Which age is the closest to the mean? All right, and which age is closest to the mean of 51.8 years? And I don't know why I just wrote a 5 because it's actually 51. Who knows what I'm doing there? All right, which age is the furthest? And that one is going to be the 44 that they gave us at the beginning, because the absolute value of negative 7.8 is going to be larger than any of the numbers. So for these questions, I don't really care what direction it is. It's just which difference is going to be the smallest and which difference is going to be the largest from there. As we get into question number 6, we're going to start looking more specifically at what we do depending on the shape of the graph. So everything leading up to 6 was just to outline to us that using a single number to describe data isn't quite that great, because you need to really look at how all the values sit around it, what type of a spread that you get. 6 is going to start talking about the graphs that are symmetric. All right, so remember that's going to be graphs like this. Wherever your middle number is, which would be a mean, the values to the right and the left are pretty much going to be looking the same in how they are distributed. Okay, so if you have a symmetric graph, the way we are going to be doing it is using values from deviation that we would have seen in 3 and 4, beginning with that type of calculation. So suppose we took some symmetric graph, which this is pretty decently symmetric that we can look at, and you took all their deviations. We now want to start to summarize that one, right? We don't want to give people tons of data. What we want to be able to give them is something small to look at, but tells a good story to it. Okay, so here's some choices on how we could describe the deviation of the data that's up there in problem number 3. Choice A, the ages of the first 6 Chief Justices were typically about 2 years from the mean of 51.8 years old. Next to that, just as a note to myself, I put the number 1 because what I wanted to say there is that, you know, if you're describing that spread as being maybe like 2 years above or 2 years below the average of 51.8, you only actually get one number within that area, which is that one that was the closest to it, right? It was only 0.8 away. So, but then everything else is well above 2. You don't even have any 3s. You got to go all the way up to the 4.2s. All right, so choice, well, let's do choice C because that one's also incorrect. The ages were typically 10 years from the mean of that. Nope. All of them are within 10. That's true. All of them are within 10, but that's not going to describe anything of use. I mean, I might as well swap that number out with 100. And well, yeah, they're all within 100 like years away from it. That they are, but it doesn't tell us anything about it. Okay, so the answer choice that we want is going to be the one right in the middle, which is 6 years from that average. All right, and then next to it, I put plus or minus. Okay, and that's not meaning like above or below the mean part there, but give or take, it's around 6. You've got a couple that are underneath, or a few of them. You've got that 0.8. You got the 4.2, which isn't too far from the 6, but it's within that kind of range, and you also got the other 4.2. But then you also get a little bit that's on the outside of it. You get the 6.8 and the 7.8. So it's about like half are in and half are outside of that number. So it's a better estimate because it's somewhere in the middle of what's the closest and what's the furthest away from it. So there actually is a single number that we can get from all the deviations that would be in the table that is our best representative of the data, and that is called the standard deviation. Now, here's the part that I'm going to be super vague in things. We're not going to teach you how to do the standard deviation. We're not going to teach you the calculation for it. It does begin with taking all those differences, and then you do a couple more steps, but depending on the amount of data you have, it can take a while to do it. So the notes say that you're going to be using technology to do this. Most of the time, what we're going to do is actually just give you the standard deviation, but I would highly encourage you at some point, maybe even like right now, just pause the video and go watch another video on how to calculate the standard deviation just to see how it's done. Okay, you don't need to master it, but just to see how it would be done. Regardless though, there is this best representative number that can be calculated, and it is called the standard deviation. Okay, so problem number 7 says that the standard deviation of the first 6 Chief Justices, their ages, is going to be 6.24 years. So it's pretty close to the 6 that they had us pick out. It was up there. Had us pick out there, but the actual calculation is 6.24. And this tells us that the ages of the first 6 Chief Justices are typically 6.24 years above or below the mean age. That's what the standard deviation does. It tells you that typically this is what we expect them to be below or above our mean value. The next part here, I don't really know why it refers to problem number 6. I think they're trying to refer back to just everything that we did at the top of the page. But look, most are within 6.24, but not all. I think that's a key characteristic. It's not all of them are within the 6.24. You're going to have a few of them that are on the outside. It is a good representative distance, though. Problems 8 and 9 are going to help us summarize our understanding of standard deviation so far. In question 8, we're going to complete some blanks here. The ages of the first 6 Chief Justices were typically 6.24 years from the mean, while the ages of the 6 most recent Chief Justices were typically 4.24 years. Okay, so they're a little bit tighter in there. Let's see if I can find that graph here. Okay, so these are the first 6, and that's the standard deviation of the 6.24. So the further part here, just a little bit tighter in there, and it's going to end up being 4.24 once that calculation is done. Oh, and that number, by the way, is just given to you up at the top, so there's no calculation for that. Sorry, I didn't mention that before. All right, the ages of the first 6 Chief Justices had more variation than the ages of the most recent. And again, if I go back to the graph, that seems to make sense, especially when you look closer to the center. Okay, in the first 6, more of your data is actually away from that center number, but in the most recent 6, more of your data is closer to the center number, so there's less variation from that mean value. All right, question number 9. What we're going to do, this is good stuff here. We're actually going to get to see that standard deviation marked off in the graph. So this is going back to the first 6, so that's what the standard deviation of the 6.24. Okay, if you take your mean value, which was that line they gave us in the graph there, and you subtract 6.24, that's going to get you to 45.56. So that is marked off right here on my graph. And if you add the 6.24 onto the 51.8, you're going to get 58.04, which is right about there that I've marked up. So here is a graphic of actually looking at the standard deviation, and you take what you can from it right now. You know, the mean, yeah, I was in the middle of this stuff in a way, right? Because it's one of our calculations for the middle type number. But there wasn't too much around it. The standard deviation is now going to grab a certain range of numbers, but when it does it, it's only going to grab so much of the data. There is going to be a little bit that's on the outside, but there's going to be a little bit on the inside. It's not really even like a half and a half sort of deal, but understand right now that the standard deviation measured in either directions is not going to take all the data. That would be called range, and we already discussed that range is not the best way to do that. Next, what we're going to do is look at how we describe the spread of data if you've got a distribution that is skewed. Okay, so standard deviation, I should point this out too before I go any further. Standard deviation, we're going to spend some time talking about it and actually doing a lot more with it, so don't think that we're totally done, but this is just to give you a general idea of where things are going. I think in this part, you're going to get a pretty solid understanding of what this 5-number summary is. You're really going to understand this one. So if you don't feel totally confident with the standard deviation, that's totally fine. Okay, if you have skewed data, for that we're going to be using the median. Right? And I talked about that over here as well, because if you use a mean value, that mean is going to get pulled in the direction that it gets skewed. So your mean could be way off to the side. If you have one value that's super large compared to everything else, your mean can get pulled. But if you use a median, it's going to stay pretty close to that high point, a little bit offset, but it is going to nicely split the data half and half. Okay, so that's the type of graphs that we're going to be looking at here. Not that you actually get to see any pictures of them. All right, let's see. There's a lot of different names that we use for this. We can call it the 5-number summary. The graph is going to be called a box plot, or box and whisker plot is what I remember it being called when I was younger. Here's what it uses though, right? 5-number summary. It uses the low number and the high number. It uses the two values that come from the range, right? So we get that included in there. It's going to use a median because we got this skewed nature to it, so that's a better representative of splitting the data. But you're also going to get two other numbers. They're called the lower quartile and the upper quartile. Basically, the lower quartile is going to be the median of the bottom half. And the upper quartile is going to be the median of the top half. And if you really think about that, here, I'll draw a little picture. You got low value to high value. The median's right in the middle. The lower quartile is going to be right in the middle of these two. The upper quartile is going to be in the median here. And you get 4 sections, right? So you get a quarter here, quarter, quarter, and quarter. So that's where the whole idea of quartile is showing up on here. However, once we actually make the graphs, it's not going to look like everything is evenly split the way that I drew it here. You're not going to have the same length segment here as there. You're not really putting lines in the middle. And that's why this thing is so useful. So here are a couple of pictures of what are called box plots, or what I remember them being called as box and whisker plots. They do refer to the word whisker here, so I think that was pretty nice because I haven't seen that in a while in textbooks. Okay, but here's the graphic, and and our data it's totally different than the stuff that we were looking at beforehand. So just reset. We're not looking at ages anymore. We're working on something involving temperature. Okay, you've got your low value and you got your high value. So if you just subtract those two numbers, you get your range. You get some value that represents how far apart these spread. And then we already talked about why that's not too helpful here. Your median is going to be your middle number. So we don't have a list of all the values. We don't have all those numbers here. But if we were able to line up all the numbers that were given, whether it were like 10 values or 100 values or whatever, the median value, the one that would be right in the middle of there, would have ended up around, I guess it's probably just a little bit more than 35. It might be just slightly over 35 degrees there. Okay, and that'd be your median. But then you take all the data that would go from that number to your high point, and if you had them listed and you just started marking them off, the middle value would end up over here. So it is not directly between the median and the high number. Okay, it's actually going to be a little bit closer to that one. All right, and that becomes your upper quartile. You do that for the bottom half and you can get a lower quartile. So it does break everything into like 4 areas. Okay, and each of those areas is worth 25% of the data. So again, kind of imagine you had a whole list of numbers. The first 4th of them sit within this range. The next fourth of them sit within this range. The next fourth sit within this range, and the last fourth sit within this range. Okay, now here's a tough part because it seems almost backwards. The spots that are very small in these graphs, like this is the smallest section, is going to be the most dense. That's going to be the area where there's 25% of the data that has the least amount of variation. The sections that have the bigger, this is probably the biggest one right here. The biggest range is going to be the least dense. It's going to be more spread out within that area. All right, here's another graph. I don't know if it's supposed to go, it looks like it might be the same data. It's just kind of turned on its side there. Maybe it's not, it might be my imagination, but here's another picture. The reason that this one got included was to show you this part right here. All right, the median is the middle of the data. Okay, half of the data is above the median, half of the data is below the median. Oh, and by the way, you can make a graph sideways. Most of them look like this, but sometimes you'll see them vertical. Half of the data is below the median, half of the data is above the median. But if you just grab the quartiles that are right around it, you get this neat sort of thing here that within this box is 50% of the data. Half of the data in the middle is in this area. So there's a lot of things that you might want to look at. I mean, obviously, like we've studied things with data where you have outliers. So sometimes the parts that are over here, and this is called the whisker part. This is the box, obviously, and these are the whiskers. If the whiskers are really long, then what that tells you is that you have some outliers in there. And you might not really want to pay much attention to it. You might want to look closer to what's going on around the median, because we're always trying to summarize data and give the best picture to people that we can, the best idea of what's happening. All right, for the remaining part of the activity, we get to create box plots. You actually get to try some stuff out, which I think you're gonna like because with the standard deviation stuff, we didn't actually get to create anything. We just sort of thought about it and we tried to describe what it meant to ourselves. But in this part, it's gonna be more tangible because you actually get to try it out. You get to see some things. Okay, for the first question, we're not going to build anything. We're just going to practice on how to read it. So this would be your box and whisker plot. You've got your median in the middle of the box. You've got your lower and your upper quartiles. You've also got minimums and maximums. And all you really got to do is, so you need to understand what these little areas are or the transitions are, but you just match them up with the x-axis, and those are your numbers. So your minimum value, and you just estimate, I called it 18,000. The maximum value I got as about 160,000. I think it was right at that spot. The median is going to be, I called it 49,000, lower quartile and upper quartile. Hopefully I measured those off correctly there. But more importantly, I think the order that I did all the numbers is the way that I'm going to do these when I actually build them as well. I'm always going to be looking for the low and the high numbers first. Gonna mark those off. And then next I'm gonna be looking for the median, and then you go to your lower and upper quartiles in either order. But that tends to be the flow in how you build the graphs as well. Okay, so 2 and 3, we get to build two graphs that are gonna represent commute times for people who live in Austin and commute times for people who live in Houston. Okay, in order, so you get your 5-number summary, and you need that before you can make the graph. We're going to make the graphs in a little bit, but you have to have these numbers before you can make that graph. Okay, I start with the low number and I just write it down, and the high number and you write it down. Those would be the first two things. The next would be the median. Okay, so you've got all your numbers lined up in order from least to greatest. You just start from the ends, you just move in, move in, move in, move in, move in, move in, until you get to a single number in the middle, and that one would be your median. By the way, problems can vary a little bit whether you have an odd number of items versus having an even number of items, and that's why we're looking at 2 examples right now. Okay, not just extra practice, but we want to highlight that difference between the odd and the even. Okay, so I got my high, low, I've got my median here. All right, next, if your median is one of your numbers, which it was here because I had an odd amount, if it's one of your numbers, then when you do your lower and your upper quartiles, you remove that from the data. Okay, so let's get a ruler to do it. So I'm actually going to cover up the median, anything greater. And now I'm going to look at the numbers that are underneath. Okay, so you don't remove the lowest number. That's important. I'm taking out the median here, but I'm still keeping my lowest number that's not removed. And then you find the median of these numbers. So not those two, not those two, not those two, and it's at that one there, 10. And that's my lower quartile. Upper quartile is the exact opposite. Again, because we used our median, we're gonna cover it up and we're just gonna find the middle of these numbers, still including your maximum. Okay, so take them out, take them out, take them out, and you're left with a 30. That'll be your upper quartile. Okay, so then it gets a little bit tricky if you have even numbers and how you deal with it. You still begin with your minimum and your maximum and just write those numbers down. Okay, but since we have an even number of items, you have 20, that means that your median is actually sitting between your 10th and your 11th number. So I count these off, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that'd be 10, and then this would also be 10. All right, so your median is gonna sit right between these two numbers. It will be the average between these two. Now, in this case, it's pretty obvious that that average is gonna be 20. So you write it down. But if you had two different numbers, you would just take their average. Okay, so that's how you get your median. But since your median is not one of your data points technically, because we're taking the average of these two numbers, you don't actually need to cover up all of those numbers. All right, you're only gonna cover up the top 10 and then leave the bottom 10. You only cover up the median if it got used, and that'd be in an odd set. So now I've got the 10 on the bottom, all right, and then we'll find the middle of those. And again, because this is an even set of numbers, 10 is even, you're gonna go all the way to the 5 and 6 number, 5th and 6th number, and then take their average. Again, conveniently here, they're both 15, so their average will be 15. Now it is possible to have an even set of data at the very beginning and then this be an odd amount. That's possible. Okay, so there's this kind of combinations that you can create between problems 2 and 3. All right, on the top half, you finally get to do a true average in here because it falls between the 40 and the 45. So the average of 40 and 45 will be 42.5. All right, so here are the box and whisker plots that go along with the commute times for Austin and Houston. Typically, the graphs are shown horizontally, and you might see them stacked above each other, but maybe with the Austin and Houston over here, and then they're stacked, but occasionally you do see them this way of being vertical. All right, the big takeaway from the beginning here is Houston's data is more spread out than what Austin's data is. I think that would be the most obvious thing that we see first. But we have to be careful how much weight we put into that, because all that's really referring to is range, right? The max minus the minimum and the range. And then from the very beginning of the notes, he said, that's okay. It's fine to give that information, but it doesn't explain everything that's going on in here. So we had some questions to answer, and I don't think that I quite answered all the questions the way that they really intended, but unless their intention was just to get you thinking about stuff and saying a few things. All right, shapes, were they different or were they similar? That very first question is like, I don't know. Well, they look different. I mean, they're both box plots, but one seems to be more stretched out than the other one. And then they say, were they symmetric or skewed? And what do we do with that? Well, they're both a little bit skewed because in their own nature, they're not symmetric. However, Houston's going to be a little bit more skewed. So here's what I wrote, though. They both look different, but are both skewed at the higher ends, right? See, that whisker right here is really long. That means, I mean, you might have a lot of data that's here and then just one single point that's really far out there and it pulls it in that direction. And Austin, kind of the same thing, but just not as exaggerated. I mean, this is obviously the longest piece of the graph, so that 25% is less dense than you're going to see in any of the other ones that you have on there. What else? Right. They also have 50% within 5 to 20 minutes. Oh, that was a good observation here, is that from their low end to their median, that's 25% and 25% there. So on the bottom half, The bottom 25% was from 5 to 20, just like this one was here. So let me bring up the actual numbers. So all these numbers are on the graph, but we actually get to see them. But look, 50% of the data is from 5 to 20, 50% of the data is from 5 to 20. It's on the top half where they're both getting skewed. The difference, and even these numbers aren't like too far apart. I mean, they're different, but they're not way too far apart. The biggest change up here is that high value that you've got in Houston. That 85 is 20 minutes greater than the highest number here, and it's almost 20 minutes greater than the highest number that you've got there. So it seems like we've got this one single outlier in all that. All right, question B, the centers, are they the same? Actually, they were. They were both at 20 minutes, which was right here and here. I don't know how well I got those lined up, but they're both right there. So the center's the same thing. It's just the spreads are different. All right, C, variation. What does this mean about how the commute times vary in the cities? Houston has more variation. That's true. But it might not be based on, I mean, the data only had 15 and 20 people that we're looking at for each of the cities. So it could come down to the fact that you've got 1 or 2 data points that are just like skewed, right? Go back to the numbers one more time. That 85 being a single value is going to change how the graph looks. Now, the good thing is it doesn't change all the parts of the graph, right? If all we're talking about is like trying to take an average, like a mean, it can dramatically change it by being this outlier number. But what we really see here is it just stretches out that one whisker. So we can look at that whisker and say, okay, well, obviously there's an outlier involved here. The data is really spread out. So if we don't look at that part, we maybe look at the middle 50%, the box area of it, there's still not as much of a difference that's in there. I mean, yes, that part's higher than this one, but they do have the same median, right? 50% built around that number, and I don't know, it's all a little bit debatable. I mean, there's a lot to look at, there's a lot to be told about it, and in my opinion, I like these. I think they're pretty neat because there's a lot that we can describe about it. Here's your big takeaway, though, that I want you to remember as we move forward with stuff. The smaller the section is, like this, or right here, the more dense it is, the more numbers sit in that area. The more stretched out it is, the more spread out it is, the more variation there is in that area. These numbers are not very dense. They're not close to each other.